Hello students. So today we are going to study a new chapter under inorganic chemistry, that is D and F block elements. Actually you know that CBSE has revised their syllabus, right? So they have removed the topic F block elements from this particular chapter, but still we call the chapter's name as the D and F block elements. But we are studying mainly about the D block elements in this chapter. Okay, so what is this D block elements, or what are we call it as the transition elements, right? So we call D and F block elements as the transition elements or the inner transition elements, right? So since we are studying only about the D block elements, we can discuss about the transition elements. What is this D block elements or the transition elements? The first point is that all those elements in which the last electron, that is a penultimate electron, the last electron, if it is going to the D subshell, if the valence electrons are going to the D subshell, then we call such elements as the D block elements, right? Then what is the general electronic configuration of D block elements? The general electronic configuration of D block element is n-1 D 1 to 10 ns 1 to 2, okay, where n is the last shell or the penultimate shell. Okay, the general electronic configuration is n-1 d 1 to 10 ns 1 to 2. Okay, now why do we call these elements as a transition elements? We call these elements, D block elements, as a transition elements because all the properties of the D block elements are in transition between that of S block elements and the P block elements. We know that D block elements, its position, the position of the D block elements is between that of the S block and the P block elements. So its properties are also in between that of the S block elements and the P block elements. Hence we call such elements as the transition elements. Okay, we call such as the transition elements. Okay, now we consider the number of periods in a transition elements, number of periods. Okay, we say that horizontal rows, we call it as the periods. So there we are studying mainly about 4 periods in the transition elements. There are mainly 4 transition series. 4 series are there in the transition elements. We know that from group 3 to 12 we call it as from group 3 to 12 we call it as a transition elements. So there are mainly 4 transition series. First transition series we call it as the 3D transition elements or the 3D series because electrons are entering into the 3D subshell. So its electrons are starting from scandium to zinc. Then the second transition series, or we call it as a 4D series. It is starting from yttrium to cadmium. Then the third transition series, or we call it as the 5D series, which are the elements present over here is lanthanum, hafnium to mercury. Then we have fourth transition series, or we call it as the 6D series. It is starting from actinium, but that period or that series is not yet completed. It is incomplete. So we say that starting from actinium. So these are the 4 transition series: 3D series, 4D series, 5D series, and 6D series. So we are going to study about the chemical properties of these transition elements. One by one we will study about the chemical properties of these transition elements. How can you define a transition element? A transition element is defined as an element which has incompletely filled d orbitals in its ground state or in any of its oxidation states. Even if they are in the ionic state, they should have an incompletely filled d orbital. Those elements we call it as a transition element. So we can discuss the first property of the transition elements, that is the atomic radii or the ionic radii. So atomic radii of the transition elements,
The atomic radii of the transition elements is in between that of the s block elements and p block elements. So the atomic radii of transition elements is less than that of the s block elements and greater than that of the p block element. So it is in between that of the s block and the p block elements. Okay, so now we consider the atomic radii of the transition elements when we go across a pedal. So in a transition, the transition elements, as the number of atomic numbers are increasing, the atomic radii first it will get decrease, and when we go after some time it will become almost constant, then it will gradually increase. So this is how the atomic radii of the transition elements go when we go across a transition series. First it will get decreased, then after some time it will be almost constant, then it will get increased also. Okay, so now we can check the reason behind this deviation. Okay, so the first one is that when we go across a period in a particular transition series, first it will get decrease. So decrease in the atomic radii of the transition elements, as we have discussed, it is because of the increase in the effective nuclear charge, right? Effective nuclear charge. We know that when the atomic numbers are increasing, the effective nuclear charges increases. When the effective nuclear charges increases, what will happen? The attraction between the nucleus and the last shell, it also will get increased, right? With the increase in the effective nuclear charge, the force of attraction between the nucleus and the last valence shell electrons are become increases, thereby decreasing the atomic radii of the elements. Right? After some time we can see that it will become almost constant. What is the reason behind that? There is no difference in their atomic radii of the elements when we come to the middle portion. The reason for that is when the number of electrons are increasing, the number of electrons which is entering into the n-1 d subshell also will be increasing, right? More and more electrons will come to the n-1 d subshell. So what will happen? More number of electrons are there in the n-1 d subshell. So the screening effect also will be increases, right? The screening effect of the d electrons on the outermost electrons also will get increased. So this increase in the screening effect, it will counterbalance the increase in the nuclear charge also. It will counterbalance the increase in the effective nuclear charge also, right? So even if the nuclear charges are increasing, there will be increase in the screening effect also. So these two effects will get nullified with each other. So what will happen that time? In the middle of that particular series, the atomic radii will be almost constant. Okay, so the last one is when the atomic numbers are increasing, again we know that n-1 d electrons, so many electrons are entering into the d subshell, right? So many electrons are entering into the d orbitals. We know that d orbitals can accommodate maximum of 10 electrons. That all we have studied, right? The pairing of the electrons in the d orbitals of the penultimate shell, it will occur only after the d subshell is half filled, right? So there is 5 orbitals over here, right? 5 orbitals are there. So first what will happen? All the shells, all the orbitals will get filled, then only what will happen? The pairing will take place, right? So it can accommodate maximum of 10 electrons. Lot of electrons are there in the d orbitals, d subshell, right? So because of the increase in the number of electrons, what will happen? There arises an electron repulsion, right? So electrons which is present in the d subshell or the d orbitals will undergo electron-electron repulsion. So when this electron-electron repulsion is becoming more and more, it will become very dominant towards the end of the series, right? So that is why we are saying that the atomic radii are increasing when we go across the at the end. Towards the end, what will happen? It will become very dominant. Hence, the atomic radii increases also. So when the electron-electron repulsions are increases, it will cause the expansion of the electron cloud and resulting in the increase in their atomic size also. Okay, so this is about the atomic radii. So transition elements atomic radii lies in between that of the S block and the P block. At the first, it will get decreased when we go. This is how we are going across a transition series. First it will get decreased, in the middle it will be almost constant, and again it will get increased. What is the reason for each of these things? First, it will because decrease in the atomic radii, it is because of the increase in the effective nuclear charge. More effective nuclear charge, more will be the force of attraction and less will be its atomic sizes. In the middle, it will become almost constant because more and more electrons are entering into the n-1 d subshell. So screening effect arises. Screening effect will counterbalance the increase in the nuclear charge, hence will result in almost as a constant atomic radii. After some time, when more and more electrons are entering, with the increase in the atomic numbers, what will happen means electron-electron repulsion arises. So more electron, there will be expansion in the electron. We can say like that, expansion in the electron cloud. It will result in the increase in the atomic radii. Next property of the transition elements that we are going to discuss is about the ionization energy. So we can look at how does ionization energy vary for a transition element. So the first ionization energy. The first ionization energy of the transition elements is lying in between that of the S block elements and the P block element. So this is a transition. I am representing it as T. Okay, transition elements. So transition elements ionization energy is greater than that of the S block element but is less than that of the P block element. Okay, so the ionization energy of the transition element is higher than those of the S block element but is lower than that of the P block elements. Okay, so when we take a particular transition series with the increase in the atomic number, so when the atomic number increases, ionization energy also increases. Okay, so in a particular transition series, when the atomic number increases, ionization energy also will get increased. Some irregularities are there. When we avoid certain irregularities are there. Otherwise, what will happen means ionization energy is increasing. So we can check what is the reason behind that. Okay, so when we go across a transition series, we can say that its atomic number is increasing, right? So its atomic number increases. So what will happen to its nuclear charge? What will happen to its nuclear charge? Its nuclear charge also will get increases. So when the nuclear charge is increasing, the attraction of the nucleus with that of the outermost electrons also will get increased, right? With the increase in the nuclear charge. So when the nuclear charge is increasing, the attraction between the nucleus and the last shell also will get increased. So we need to provide lot of energy to remove out the electron from its last shell, right? We know that ionization energy is the energy required to remove the last shell electrons, right? So when the force between the nucleus and the last shell is more means we need to provide lot of energy for that electron to get pulled away from its valence shell. Okay, so the reason behind increase in the ionization energy is the increase in the atomic number. Its nuclear charges increases, so force of attraction between the nucleus and the outermost shell also gets increases. Hence what will happen? Hence ionization energy increases. Okay, after some time when we go across a transition series, after some time you can see that increase in the ionization energy will become small. The increase in the ionization energy is becoming very small. Even though it is increasing, sometimes it will be almost constant. There will be some irregularities happening over here. The increase in the ionization energy is becoming small. What is the reason for that? The reason for that is when we go across a transition series, what will happen? More and more d electrons are forming over here. More and more electrons enter into the d subshell. So what will happen at that time? The screening effect increases. So what will happen means the screening effect increases. So when the screening effect is increases means the screening effect is increasing means they will shield the outer electrons very much, right? They will shield the outer electrons very much from the force of attraction of the nucleus. So more and more d subshell is forming, d electrons are forming over here. So what will they do is they will protect, they will shield the outermost electron from the pull of the nucleus. So what will happen? The increase. So what will happen? So the increase is very small. So the increase in the ionization energy is becoming very small. Okay, so that's about ionization energy. The first ionization energy of the transition series. This is what the transition series is in between that of the S block and the P block. So when the atomic number increases, ionization energy increases in a given transition series. When we go across in a given transition series. Given transition series. So in a given transition series, when we go across a period, when the atomic number increases, ionization energy increases. But there are certain irregularities also. What is the reason for that? Is that when the atomic number increases, nuclear charge increases, so the attraction towards the outermost electron increases. So hence more energy is required to pull away the electron from its last shell. Hence ionization energy is increasing. There is an increase in the ionization energies become small when we go across a transition series. Why is it so? Because more and more d electrons are forming, so screening effect increases. So it will shield the outermost electron very much. Then what will happen? So hence the increase in the ionization energy will become small. Because what will happen over here? This shielding effect, this screening effect will, this we have studied in the last property. The screening effect will nullify the effect of increase in the nuclear charge, right? So nuclear charge also is increasing, but the screening effect is also increasing, so their effect is getting nullified. That is why we are saying that increase is becoming very small. So the next property is the metallic character. All the transition elements are metallic in nature. All the transition elements are metallic in nature. But their metallic character will get decreased. That is electropositive character. Their electropositive character decreases when we move from left to right in a transition series. Okay, so their electropositive character will get, electropositive means we know that metals are electropositive in nature. So their electropositive character will get decreased from left to right in a transition series. And their metallic bonding, the metallic bonding in a transition element is very strong. They are very strong. The metallic bonding in a transition element is very strong. What are the reasons for that? What are the main reasons for the strong metallic bonding in transition elements? It is because of the greater effective nuclear charge. Their effective nuclear charge is very high, right? Transition elements are having higher atomic number, so they are effective, they are having higher effective nuclear charges, but they are ionization energies. Ionization energies comparatively they are having lesser ionization energy. So ionization energy is less and the effective nuclear charge is great. So this is the two main reason. What is the next reason for that is that so effective nuclear charge is greater and lower ionization energy, and there are lot of vacant d orbitals. They have lot of vacant d orbitals in the outermost shell, so they can form the very strong metallic bonding. Okay, so the reason for the strong metallic bonding is the greater effective nuclear charge, lesser ionization energies, and the presence of vacant d orbitals in their outermost shell. And because of the presence of very strong metallic bonding, these are possessing these transition elements. Most of the transition elements are very hard, right? They are very hard. When you compare to the other elements, they are very hard. It is because of the presence of the stronger metallic bonding. They are very hard and they possess high density. Their density is very high. They possess high density. The next thing is that their enthalpy of atomization. Their enthalpy of atomization is also high. Comparatively, it is very high. It is all because of the stronger metallic bonding. So all majority of the transition elements are metallic in nature. Their electropositive character decreases when we go across a transition series, and their metallic bonding is very strong. What are the reasons for that? These are the three reasons, right? Their presence of greater effective nuclear charge, lesser ionization energies, and presence of vacant d orbitals in the outermost shell. And it is because of the stronger metallic bonding, majority, or we can say that all the transition elements are very hard. They possess high density. Their enthalpy of atomization is also very high. The next property is the oxidation states. All the transition elements except the first and the last member. The first and the last member of a transition series exhibit variable oxidation state. This is an important property of the transition elements, the occurrence or the exhibition of variable oxidation state. All the transition elements has the capacity to exhibit more than one oxidation state. That is what we call it as a variable oxidation state. We have studied in our lower grades itself certain transition elements. We have studied about the iron. Iron can exhibit, or the copper can exhibit more than one oxidation state. That's what we call it as a variable oxidation state. Except the first and the last member, all the transition elements can have a variable oxidation state. What is the reason for that? The reason for the variable oxidation state is that both the electrons of the n-1d subshell and the ns orbital can take part in the bond formation. Both the electrons from both the orbitals can take part because of the comparable energies. Both the orbitals have somewhat same energy. Because of the similarity, because of the comparable energies of the n-1d orbital and the ns orbital, electrons from both the orbitals can take part in the bond formation. So what will happen? It will result in the variable oxidation state. Okay, the common oxidation state of the first series is +3. This is the +3 is the common oxidation state. This has been asked many times. Common oxidation state of the first transition series is +3, except scandium. Scandium is the first element, right? So except scandium, the common oxidation state that is exhibited by the first series is the +3 itself. The next question they have been asked is about the highest oxidation state. Highest oxidation state exhibited by the transition element is +8. plus 8, and it is 8 itself. Okay, the highest oxidation state of a transition element is 8. It is exhibited by the osmium and ruthenium, Ru and Os. Both of these elements are exhibiting the plus 8 oxidation state. Okay, the next thing that we need to study is that mostly those elements which are exhibiting plus 2 and plus 3 oxidation state, they are mostly, it will be in the ionic state. And higher oxidation state, those elements which are having higher oxidation state, and commonly it will be covalent in nature. It will be covalent nature. Okay, so for example, ZnCl2. ZnCl2 is ionic in nature, right? And CdCl2. These are all examples of the compounds with the plus 2 and plus 3 oxidation state, which are ionic compounds. And another way, chromium Cr2O7 2 minus. For example, K2Cr2 and potassium dichromate KMnO4, that is MnO4 minus. These all elements are no covalent in nature. Okay, these all are covalent in nature. Okay, so and transition elements can even exhibit zero oxidation state. It can even exhibit zero oxidation state. Zero oxidation states are exhibited by certain coordination compounds. For example, nickel NiCO4 carbonyl compounds. Nickel carbonyl compounds can exhibit an oxidation. Nickel, here it is the transition elements of nickel. Nickel can exhibit an oxidation state of 0. Then FeCO5. Here also ion is exhibiting an oxidation state of 0. Okay, so a lot of questions have been asked from this part. The first thing that you need to know is, it is exhibiting, transition elements are exhibiting variable oxidation state. Why it is exhibiting variable oxidation state is that both the electrons of the n-1d orbital and the ns orbital can take part in the bond formation because they have the comparable energies. So it is exhibiting different oxidation state. The common oxidation state exhibited by the first transition series is plus 3, and the highest oxidation state that is exhibited by the transition element is 8. Okay, it is exhibited by the osmium and ruthenium. Then those compounds which are having lower oxidation states such as plus 2 and plus 3 are ionic in nature, but those are having higher oxidation states are covalent in nature. Transition elements can even exhibit zero oxidation state.